Hey everyone, so this is the last thermodynamics type lecture. So what we're going to talk about is the second and then later on the third law of thermodynamics. So we're going to take what we kind of talked about in the previous one where we started talking about some of the processes and we're going to apply that to engines. All right. So the first law basically tells us that energy is conserved. That was like the main idea, saying that, you know, the amount of energy that internal energy that an object gains is going to be equal to the sum of the heat added and the work done on it, essentially. So it kind of just stems from the idea of conservation of energy. However, there are different scenarios where we technically have conserved energy, but we would never see it in nature. So the question is, well, why does this happen? And that's where the second and third law comes into play. So consider a case like this: we have a cup that is completely broken, and then all of a sudden it reassembles and then comes back on top of the table. Now we can say that, well, this is kind of conserved energy. However, it would never happen in real life. Maybe not this exact case, but there are other scenarios like that. So the question is why? Well, the second law of thermodynamics is a way of telling which processes would occur in nature and which ones wouldn't. The second law states that heat flows spontaneously from a hot object to a cold object, and heat will not spontaneously flow from a cold object to a hot. So basically, the idea is saying that heat goes from high temperature to low temperature, always. It never goes the other way around. Um, and a lot, like I said, a lot of this stuff comes from heat engines. So a heat engine is something that's going to take advantage of this second law that takes advantage of the fact that heat is naturally going from a high source to a low source and is using that in order to gain mechanical work from it. That's what we're referring to when we say heat engines. So, for example, um, here we have a high temperature source. Heat's going to naturally go to the low temperature source, but what we do is we use an engine and we create a device here so that some of this heat actually goes towards the form of work. So that's kind of what the engine's doing. Now you're going to see diagrams like this to kind of show how the energy is flowing. I'll explain in a second kind of what a physical engine would look like that's doing this. Um, but yeah, yeah, even though we knew about thermal energy for a while, it took us a while to actually create something that would end up taking advantage of heat. It took us until the 1700s with steam engines. So, um, what we're going to do is we're going to consider engines that occur in repeating cycles. So they're going to end up running consistently and continuously. Realistically, after a while, the engine will start to wear down, but we're going to take the simple case and we're just going to assume that the engine starts at a specific scenario, it's going to run, and then it's going to return back to that original situation. Because of the fact that the engine is going to start and end its cycle at the exact same state, we're going to say that its change in internal energy is always going to be equal to zero from the entire cycle. So when it returns back to that initial state, the internal energy becomes zero again. Remember, this is because of the fact that the equation for internal energy is based off of the temperature. And if we're ending at the same state, then we're ending with the same temperature. This is one of the things that they refer to as a state variable. Temperature is what's called a state variable because if it goes to its original, pressure and volume and number of moles, then its temperature is also going to be the same. So what we're going to say is that for the heat engine, this equation is going to be true. The amount of heat that is leaving the high reservoir is going to be equal to the work being done and the heat going to the low reservoir. Um, Now, the temperature that this is at and the temperature that this is at are sometimes called operating temperatures. Um, what we're going to do is we're going to end up coming up with an equation that also talks about that as well, since it is kind of hard to talk about, you know, the heat being transferred from one state to another. Instead, we can refer to what's going on with the temperatures. One thing to note is the signs are going to be different. Everything's positive here because the heat is leaving this, the heat's going to here, and energy is going to work. So all these numbers are going to be positive. A lot of times, what you have is a material that ends up being heated and cooled. This is what's usually called as a working substance. You'll see some examples later on. This in this example, the working substance would be the gas air mixture, but this is one example of a heat engine. So you have uh, gas and air being pushed into this canister. Because of the intake of all this gas air, it's going to push this piston down. The piston's going to swing over, and then due to its momentum, will then fly back up towards compressing the gas again. By compressing it, it not only heats up the gas, but it will also ignite this spark plug, which then ignites the gas. The igniting of the gas causes the gas to expand once again, pushing the piston down. And as it swings back around and goes upwards, it then pushes the expended gas air out of the exhaust pipe. So this is one example of the whole heat engine that we're using the heat that is being used to from igniting this gas and the heat that goes outwards to move a piston around. This is more like basic type way of doing it. So here you end up having these pipes and they use steam. The steam will actually cause the air to go up and around. And as it does that, it will actually start to push pistons around, getting work. This one's another one. You have high pressure steam moving towards low pressure steam. But in order to actually get to that low pressure, it has to push a turbine out of the way. So again, naturally the heat wants to go from this point to this point, and we just put something in the middle to kind of get a little bit of work out. Pretty much anytime you cause something to spin and rotate, you're going to end up getting mechanical work out of it. Um, all right. And from all these, you can easily tell that there has to be some sort of temperature difference in order for the engine to run, because otherwise, you wouldn't have gas wanting to move from one point to another without this temperature difference. All right, we have a thing called efficiency. So we can talk about how efficient an engine is based off of the amount of work that we get based off of how much heat ends up being put into the system. So we define the efficiency as this ratio, how much work the engine's able to do and how much heat is required. If these two numbers are the same, then that means we have a 100% efficient engine, something that uses all that heat and goes straight into work with no exhaust. So what we end up having are these two equations. What we can actually do is take this and combine it into the efficiency equation, and it ends up reworking like this. So you just move the QL over to here. So you have QH minus QL, plug it in for the work, and then simplify. So this is the general form, and this one also works as well. So you're going to use one or the other based off of what's given to you. All right, so one thing you've probably heard is that there's no such thing as a perfect 100% efficient engine where no heat is being exhausted to the environment. This ends up becoming super important. It basically means that there's no such thing as perpetual motion machines. Um, for those who didn't know, perpetual motion machines are ones where you put a little bit of energy into the beginning to start it running, but then it just continues to run over and over. So a lot of times you might hear people say things like, "Oh, this breaks the second law of thermodynamics." They're usually referring to this, that the efficiency, that there is always going to be some energy being lost because of natural things like friction and things like that. So uh, it is there is no such thing as a device that has the sole purpose of taking heat and transferring it completely into work. There will always be some energy being lost at work. Now, you might think, well, what if we have a 99% efficient engine? Well, what we're going to talk about in a second is that even that is kind of impossible. When we're going to see what are the actual efficiencies, or the uh, most likely efficiencies that an engine can have based off of its state variables. So we'll just practice this real quick. You can pause the video, work on this yourself, and we'll go over it in a second. All right. So one thing to note is you'll notice that they talk about how this is the amount of heat per second, and they want how much heat discharged per second. So they're actually asking for powers, but realistically, you could just divide each of those heats by time, the same time, and it works the same way. So kind of ignore if they're talking about power and energy, unless they're giving you different sets of times, which I don't think they would. But what you would do here is use the efficiency and plug it into our general equation, that it's equal to the ratio of the work over the heat lost, heat input. So we take the 23 kilojoules and we divide it by the efficiency, and we get 115 kilojoules. Because this is the amount of work done every second, that means that this is the amount of heat required every second. So you could have left it as 115 kilojoules, that's fine, or converting it to joules, that's also fine. But because they wanted it per second, I did convert it into kilowatts. So I just wanted to throw that out there. All right, so for part B, we do the same thing. We could have used the other equation. So we could have used the second law equation of that, it's QH equals W minus plus QL. That also works. You could use this one, again, whatever floats your boat. So when you're using this, when you plug the numbers in, you get 92 kilojoules, or because it's per second, 92 kilowatts. Again, the number doesn't change. All that changes is the unit. And in a case like this, I would be a little bit more lenient as to whether I would count the units or not. All right, so yeah, we're gonna find out in a second that 37% is pretty much impossible. Is the limit for most engines, and that getting something significantly higher than 37 is not likely. Typically, 20% actually is a typical efficiency for engines. This diagram here is just showing again the concept of the 100% engine, that this is not possible. All right, now one thing that I want to point out is that there are two different types of processes. So there is a reversible process, which basically means that it can be carried out so slowly that every state that it goes through is an equilibrium state, meaning that the pressures, the volumes, the temperatures are all kind of matching properly the way that they should. These are processes that could be easily graphed and properly graphed. Um, and the phrasing of reversible process basically means that it can then be reversed without the amount of work done or heat exchange changing. Um, Now, the thing is, this process does not actually exist in the real world. There is no such thing as a real world reversible process. Um, what we do instead is we treat these processes, even though they don't exist, we treat them as good approximations and limits to what we would normally see. This is pretty much like the ideal gas. Like it gives us a rough idea of what to expect. Uh, so if we're doing stuff with engines and we find out that treating it like a reversible process would give us an efficiency of 50%, then that means that a real life engine based off of this would run something below 50%, because of the fact that it's not a perfectly reversible process, but it wouldn't be anything greater. So this ends up being our limiting factor. Now, real processes are actually irreversible because they have to be completed in a finite time. There's no such thing as an infinitely slow engine. Um, but it's also because there's things like friction, turbulence, things that end up taking away some of the energy that makes it impossible for us to reverse. It's also makes it because it's also like this because um, sometimes when you have a cycle, like you might have a gas expanding, let's say, uh, isothermally, where the temperature remains the same. However, if you actually had sensors in it, you'd find that there are certain areas that may heat up more than others. You might find that there are times where the temperature does change. You might have areas where the pressure changes more drastically than the volume, and all these things. So while on the whole the temperature doesn't change too much that we can call it an isothermal process, it's not a perfect it's not perfectly isothermal at every moment. So that's what we mean by reversible versus irreversible and needing to be carried out infinitely slowly. Uh, and this kind of goes back to one of the things I said before, that irreversible process technically can't be plotted on PV diagrams. Only reversible processes can, because you would have, weird spikes all along it, and it wouldn't be a nice smooth curve. All right, so this is going to lead us into something called the Carnot engine. So the Carnot engine is looking at a very common engine cycle. Uh, I believe it's a steam engine cycle, and it takes advantage of a type of reversible cycle. So what we're going to do is, like I said, we're going to use this reversible Carnot engine cycle and try to come up with some limiting factors that we could apply to real life engines. So, like I said, you're going to think of the Carnot engine as a theoretically best engine that could possibly exist. Um, the Carnot engine operates on what's called the Carnot cycle. Who would have guessed? So this is what the Carnot cycle looks like. So there's four processes on here. So going from state A, it expands isothermally to state B. So during this process, the temperature is not changing. Now, this is the section where heat is being added to it. So heat's being added to the system, to whatever our working substance is, pretty much a gas or some sort of steam, and it's causing the gas to expand, but the temperature is not going to change. Then going from B to C, it then expands a little bit more, but now it's expanding adiabatically. So here, there's no more heat going to be added to it, but the temperature is now going to be changing. So the temperature does get reduced to TL because of the increased expansion. Now, state 3, or process 3, is another isothermal process, but now it's being compressed. So it's being compressed isothermally, in which case the heat is actually being removed from the working substance. And then the last part, to get it back to our initial state, we're going to have another adiabatic compression, bring it back to A. So during this entire process, we end up at the same spot that we started with. So our change in internal energy will always be zero when we go back to this initial state. So we end up having two isothermal and two adiabatic processes. One thing you're going to notice with a lot of these engines it tends to be two of one type and then two of another. So you might see a process that's like two isovolumetric and two isobaric, or two adiabatic and two isobaric, or two thermal and two isovolumetric, things like that. Um, so we one way that we could find the work that we end up getting, besides using these heats, because we may not know these heats, we may only know these states, is by finding the area enclosed within this diagram. Now, that would be a little bit hard because, if I'm just given this and these numbers, it might be a difficult task to actually just take the area of this since it's a very awkward shape. But what I can do instead is I can come up with equations to figure out, the work done through the isothermal process, the adiabatic process, and then subtract these compression sections, and that would give me the work. So we're actually going to try to figure that out in a bit. Now, the efficiency, this is our equation for efficiency, but for Carnot cycles, we're going to rewrite this equation so that it's based off of their state temperatures. So first, we have the isothermal process. So if you recall, this was the work done in an isothermal process. And remember, we're going back to what we talked about in the previous section with the first law of thermodynamics. So we're going to be combining a lot of that stuff right now. So this was the equation for an isothermal process for the work done. And because it's isothermal, where the temperature is not changing, the work being done is also being equal to the heat inputted. We could do the same thing for the other isothermal process and set that equal to the heat being lost by the system. Next, what we can do is through the adiabatic process. If you recall, we had this relationship that relates pressure and volume of the two states. So when it went from state B to state C, and for the other adiabatic process. Also, because of the fact that we have the ideal gas law, we know that these equations hold true. That PV over T for one state is equal to PV over T for the other state. Now what we're going to do is we're going to combine all this together so that we can find a way to combine these two together. So when I combine this with this adiabatic equation, I end up getting this. So this can be done a multitude of ways. One way is just dividing this side by this and this side by this to get these. That's why it ends up being TH gets brought up to the numerator and why it ends up being gamma minus 1, because we're dividing this by another VB. What you could have also done if you didn't want to do this is you could have moved the moved everything but PB to this side, plug this into here, and then just simplify, but you would end up with the same thing. And the same thing occurs over here. Now what we're going to do is we can set TH over TL here and TH over TL here. Or actually, what we could do is just divide this by this again. That's what we're doing here. So this TH, the VB gets divided by the VA. This TL side gets divided by the VD side. So we get this, because we end up getting VB divided by VA. The gamma minus 1 gets pulled out on both terms. Because those exponents are the same, I could just drop it. So what I get is that this VB over VA ratio is also the same as this ratio of VC over VD. What this is going to now allow me to do is find a way of relating QH and QL with TH and TL. So what I can say now is that QH, what this phrase is equal to, is also equal to VC over VD, because again, this ratio is equal to this ratio. From here, I can then say, well, NR and this equation is equal to QL over TL, and plug that in. Yeah. And you'll see the N and R's drop out, and I end up getting this. That basically this ratio is equal to this ratio. Now you might have thought like, oh, probably could have guessed that, but again, we're not trying to guess. We're trying to come up with a reasonable explanation. You're going to notice later on when we talk about a different type of engine cycle that this same process will not work. So like this works for Carnot engines, but it won't work for this will work for a Carnot engine, but it won't work for what's called an Otto engine. So this ends up giving us what's called Carnot's theorem, that basically this ends up being the limit to the maximum efficiency that an engine can have. That an engine operating at these two temperatures can only have this maximum efficiency. Any irreversible engine would have an efficiency less than this. For most real engines, they would end up having about 80% of whatever this Carnot efficiency is. So for example, if this Carnot efficiency tells you that your engine should be running at 50% efficiency, then a real engine would probably be somewhere below that at around 40 or less. All right, so here's a question dealing with the Carnot engine. Pause the video, work on this yourself, and we'll go over in a second. All right, so what we want to do is we want to figure out the general efficiency and then use the Carnot efficiency and see if it makes sense. So our general efficiency, which again, I want to reiterate that this works for any and all cycles, tells us that the efficiency that the engine's telling us is that it's 56%. Now what we're going to do is we're going to treat this as a Carnot engine and find that its efficiency is actually 34%. So the maximum efficiency is 34%, but the manufacturer is telling us that it can run at 56%. Therefore, this is violating the second law of thermodynamics. So this is one of the ways that people are trying to use the phrase when you see it online, is they're trying to refer to this concept or partially this concept. I think some of them also are using it in place of the third law of thermodynamics, of entropy. All right, so I just wanted to quickly talk about the Otto cycle. So this one's actually a little bit more like what's going on with automobile engines. Like I said, the Carnot engine's more like a steam engine. Here, this is what's going on in your car is you have it's starting at some state. You end up having, once again, 4 processes. This time you have an adiabatic compression. Then you have an isovolumetric compression. Then you have, I think that's the expansion. Doesn't really matter. Then you have an adiabatic expansion, and then you have another isovolumetric change. Now here, one of the main differences is that the temperature actually is constantly changing throughout because there are no isothermal processes. Yeah. So this just kind of goes into a little bit more detail with it. We have the heat now coming in during these isovolumetric areas and heat being lost in that section. Now we can do the same thing where we can kind of come up with an efficiency equation for this. Now the main thing is it's gonna be end up being a little bit different. So first, because these are isovolumetric areas, what we can do is we can actually use the whole NC delta T equation, which was the molar specific heat at constant volumes. And that gets us this for the efficiency, relating these temperatures. Now, because of the fact that the temperatures aren't really fixed, this also doesn't really help us. So what we have to end up doing is kind of doing something similar to what we did last time and coming up with an equation for this that's now related to things like pressure and volume, things that we actually can measure for an Otto cycle. So we do the same thing. We have the adiabatic process. This is what we get when we divide it by the ideal gas law. And then when we combine this into here, it ends up becoming this complete hodgepodge mess, where now we're only dealing with two temperatures, TC and TB. So it ends up being a little bit more crazier. You can actually try using that equation here. Pause the video, work on this yourself, and we'll go over in a second. All right. So what we're going to do first, because this is an diatomic gas, we know that the gamma term is going to be 1.4. And we know that the compression is a ratio of 8. So what we're going to say is this, that VA over VB and VD over VC is equal to 8. So when we take the Otto efficiency, we're going to plug in 8 for a lot of these ratios, or 1 over 8, I should say. And then we're going to end up getting this. Actually cleans up to be looking like this. So we can put in our ratio in for this term. We could plug in the gamma term that we're given up here. And we end up getting 56%. You notice that we don't have the temperatures, so they end up crossing out. So that's kind of one of the nice things about this, is that if we can make sure that the ratio is the same for both, which it usually is, it will typically end up simplifying to being something like this. All right, so the last thing that I want to mention really quickly are fridges and ACs and heat pumps. So the process of this is essentially taking a heat engine and running it in reverse. So instead of having the heat naturally flow from a high source to a low source, we're now going to do it the reverse way, where it's going to go from low to high. Now, unfortunately, that's violating the second law of thermodynamics, or at least it seems like it. Because remember, heat's not naturally going to flow from low to high. So what we're going to do instead is instead of getting work out of that scenario, we now have to actually put work in to bring the heat from low to high. The way I actually put it in, like the way to visualize it, is thinking like a waterfall versus an irrigation system. So a waterfall, the water naturally wants to flow from the high point to the low point, and you're basically putting something in there like a water wheel in order to get energy out. However, you can technically run the water wheel in reverse and pull all the water upwards from the bottom and lift it upwards to the top. So when you're taking advantage of the natural process of it falling down, you can get heat, you can get work out of it. But if you're trying to do something that's not natural, like lifting it back up, you pretty much have to turn the wheel and put work in order to, lift it up. And that's kind of how a lot of irrigation systems worked in the day. All right, so here is the system. So here we have a low temperature system. We do work to take heat from this low source and put it into the high temperature. Now, refrigerators, ACs, and heat pumps all work exactly the same. The only difference is where it's actually going, and I'm going to mention that in a second. So here, this actually ends up being the exhaust part. Now, one thing to point out, if anyone's ever seen the episode from SpongeBob where he accidentally left the fridge open and it ended up cooling his entire room, yeah, that's not exactly how it works. And in fact, it does the complete opposite. If you leave a fridge open, and my friend actually had done this in college, when you leave a fridge open, you would actually end up heating your room so much that it would be almost unbearable, and you'd probably end up ruining the fridge itself. But basically, what ends up happening is the fridge is working on a sensor, basically trying to keep what's inside the fridge equal to some low temperature. So it's running its compressor and running its system to take heat from here and put it into the exhaust so that this fridge remains at that temperature. Now, the thing is, the exhaust heat is the environment at this point. So your bedroom. So this is the fridge and this is the room, the kitchen or your bedroom, depending on where your fridge is. So every time the fridge is doing work and taking heat out, it's being exhausted into your room. So the longer the fridge is running, the more heat it's expelling into the room. And because the fridge door is open, the temperature will not stay cool. So the fridge is going to constantly be running until it eventually heats up the room so much that it actually can't run anymore and ends up dying. So, yeah, interesting thing. Now, obviously, a perfect fridge is one where no work is required to actually run it, which, as we know, is not possible. So one thing that we do is we actually, to talk about like the efficiency of a fridge, we're going to kind of use this concept, and we're going to talk about what's called the coefficient of performance. Basically, it's the amount of heat that gets removed divided by the work being done to remove it. So it is similar to efficiency, um, but it's being used for fridges and ACs. It's going to be slightly different for the heat pump. So what we can do is we can rework this using the second law equation to get this, or we can kind of apply a similar process for the Carnot cycle, but for the fridge, and treat it based off its temperatures, and we end up getting this. So this ends up being the ideal COP for fridges and ACs. Like I said, you could think of it as the Carnot fridge and Carnot AC. Really quickly, for those who want to know kind of what's going on in the fridge, like how it ends up working, basically what ends up happening is, despite the fact that we're saying that it's going against this second law, it actually is using the second law. So what's going on is, you have a compressor here which forcibly compresses the pressure, this vapor pressure, this liquid, and it causes it to have a very low temperature, lower than where your fridge is at. So as that low cooling substance goes through the fridge, it runs through the fridge, and it then allows for heat to flow naturally from inside the fridge into that low pressure vapor. The low pressure vapor, then once it moves through here, it's heated up at some point, and then it goes into the back coils. These back coils actually, as it goes into it, it then expands, so then it actually heats up more than it was before, and then it expels that heat into your environment. Typically, you normally want in order for a fridge to actually work, you normally want the surrounding temperature to be fairly low compared to these coils. Like if you're running your fridge in a very hot room, then this fridge is going to drop very low, and you're going to end up burning your compressor. So it's these two things going on. You're basically causing the temperature to drop by having a very low pressure vapor, and then heat flows from the fridge into the coil. Then it goes to the outside where it expands and becomes high pressure, and then the heat gets pulled out, and then it just keeps repeating that cycle. Now, heat pumps basically work the exact same way, except instead of you being on this side, you're actually on this side. So essentially, treating a heat pump would be like taking your AC and flipping it. So you have the cooling section on the outside, and then you have the heating section, the exhaust, inside your room. So that's how a heat pump works. It's still taking heat from a cold source to a hot source. It's just that now the hot source is where we want to be rather than the other side. Because of the fact that this is now what we're looking for, the COP actually changes. So now it's QH over Q over W. So it's still the idea of like what we're looking at divided by the work needed. It's just that now we're looking at how much heat we can get rather than how much heat we can remove. And then it ends up reworking like this. So you could pause the video, work on this yourself, and we'll go over it in a second. All right, so we want to know how much heat can be added to this room per second. What we're going to do is use the equation for COP. We know that it's equal to 3. Again, because it's per second, it doesn't really matter. The numbers don't change. So just take the amount of work done every second, times it by 3, and we get 4,500 watts. So that's how much heat can be added to the room every second. All right, pause video, work on this yourself, and we'll go over in a second. All right, so we want to know how long it would take to freeze an ice cube tray. So this is actually combining what we talked about in pretty much, I believe it was the first or second lecture on thermodynamics. But what we're going to do is we're going to set this, the QL that is needed to be removed from the system, and set it equal to the heat, the amount of heat needed to phase change the ice. So in order to phase change the ice, we need to remove this amount of heat from the water. So this is going to be equal to my QL. So using this and setting it equal to my the COP, I get this. Oh, so this is because of work over second. So what you could have done is done it slightly differently, and basically figured out, yeah, so this is just taking advantage of power. So power is 200 watts, watts over work over time, and then setting that equal to QL over COP. You could have, like I said, done this in a slightly reverse way, where you use these numbers to figure out the work and then put it into power. Again, whatever floats your boat, but you should have gotten 260 seconds for the amount of time. All right, so that's it for these cycles. What we're going to talk about in the next part is how this now plays into what's called entropy. If you have any questions, please let me know. Otherwise, I'll see you in the next one.